For multiple dose kinetic determination of Vmax and Km, what we do usually, the rate of the metabolism or elimination at steady state, we said that at multiple doses, whatsoever the route of administration we are considered, or we are the most critical concentration that we need is the steady state concentration, in which we want to determine the target concentration in clinical practice. So this is what is important for us. At steady state, we know that the input that we have should be equal to the output that we have. So accordingly, we know that the Michaelis-Menten equation is why? Because we just substitute the concentration of the drug here with the steady state concentration. Okay, so we have a steady state concentration here, so this is one difference, which will be equal the rate of metabolism or the rate of elimination. Okay, at steady state, which we had our measurement on it, we know that the input equals the output, so we are assuming that the rate of elimination should be equal to the dosing rate, okay, which means the input. The output is the elimination and the input is dosing rate. We call it as R equal V equal Vmax multiplied steady state concentration over Km plus steady state concentration. So again, this is a difference and this is a difference. So it ends up, and this usually is either dose per time, or we just say mass per time. And again, it's the same unit as this. So R equals Vmax so this is the how we represent multiple doses kinetic for multiple doses nonlinear kinetic to determine now the parameters that we have. There's different way of dealing with the Michaelis-Menten equation for multiple doses. One of the simplest way is to take this, rearrange it in a way to have it linearly, and you have it on your slide. Okay, so again, just it's a rearrangement of the equation, so you have it as linear equation, so you can deal with it. If we have this versus this, you can have a profile, and again, just make sure that you know that this is a dosing rate of your profile. If you have this equation, again, if you have this equation as R V max minus Km, and you will have R as, let's say, milligram per, you have it on your slide as milligram per day, but it's mass versus time. Okay. Okay, and this is will be R over steady state concentration, okay, which will be not multiplied over our concentration, which is mass over volume. Okay, so it will be equal to volume per time. Okay, so according to this, we will have, again, you can do linear regression, ax plus b equals y, but we have this as positive, but we have we have this as negative, and we have this as positive. So what will be the shape of the line that you have? You will have it decreasing, right? And this will be your y-intercept, and you can do a linear regression to have the slope of your profile. Okay, according to whatever we have in the equation, we have this as the slope, and it will be minus km, and we will have this as the y-intercept. So if you have the equation, if you have different data sets, you have the equation, you can determine this, which is minus km, and you can determine this, which is Vmax. Okay. If you have in your slide or not that we need at least two to have the line, right? We need at least 2 doses, and for sure to have 3 or more is better to have more accurate calculation. So you need to have more 2 or more dosing regimen, dosing rate, and you have to have 2 or more steady states measured concentration, so you can determine those kind of things. So you either determine the slope or intercept, and you can go back to the equation and apply it to determine the other parameter. So if you have the slope, you can just go and apply it here, or you have the linear regression and have both of them together, and we will see this in the questions that you have. Okay. For nonlinear kinetic, also you need to make sure that one thing that we kept saying during the semester, that when we have linear kinetic, you have constant for linear kinetic, you have constant half-life, you have constant K, and you have constant clearance, and also area under the curve was proportionally related to the dose. None of those, as I said, are valid anymore. So accordingly, for nonlinear kinetic, we were using those as main parameters to define the model. For nonlinear kinetic, those are not valid anymore. So the clearance is not constant, the elimination rate constant is not constant, and even the half-life is not constant. So we can't use any of those as mean parameters to define the model. And also the area under the curve is not anymore proportional to the dose, as we saw in the profile, in which I said that it will be deviating from linearity. And still, even the time to reach a steady state, not as simple as what we have in the linear kinetic, but still we determine the time to reach 90% of the steady state in a way to make it easier to present the time that we need to measure some of the steady state concentration in the dosing regimen that we have. And you have the equation on your slide, in which you have this over Vmax minus R squared, don't forget the square, 2.303 Vmax minus 0.9 R, which will give you the time to reach 90% of the steady state. Okay, so again, we have Km. You know what is Km? You have Vmax dosing rate, Vmax or R dosing rate, and this is the volume distribution, and it depends on the model depending on the units that you are using, the unit of this will be determined. I'm adding as days on your slides, but again, it depends on whatever that you have. If this is mass per day, then this will be days. If not, it will be different. Okay. The profile that you have in which you have plasma. One second. You have plasma concentration versus time for different dosing rate. Okay, and then you have it like this versus like this, and then each time the time to reach the steady state is changing. Okay, and there is small arrows like this, like this, and like this, and like this, which is the time to reach 90% of the steady state with those arrows. Okay, and you can notice that each profile, there's numbers on them, which is rate of administration. Okay, which means that it's R in mass, which is milligram per day. Okay, and on each one of them. So we have here R equal 300, here it's 350, 400, and 425. Okay, and for that you can notice that time to reach 90% of the steady state, again, which we use it usually in practice according to this equation to determine the time that we need to do the measurement to adjust the doses or the rate of the administration or whatsoever, tau if you have multiple doses. We usually need to determine time to reach a steady state. As R is increasing, the time to reach the steady state is changing. Okay, so higher doses or dosing regimen causing higher concentration in the plasma, which is causing reaching the steady state in a longer time compared to the low doses or dosing rates. In other words, if this is increased, okay, then all of that will be number minus a larger number will be decreased, then the total will be increasing. So again, you can just know that as the from this equation, either you have it from this equation or you just know as the dosing rate is increasing, then the time to reach the steady state will be longer or later than usual. Okay, I will stop here.